So this is Einstein, as you can tell. And the point here is that when we got postulate 1 and postulate 2 together, postulate 1, physics should be the same in all inertial reference frames. Postulate 2, the speed of light is independent of reference frame. That Galilean transformation no longer works, and Einstein says we need a new transformation. So Einstein also says, hey, the Galilean transformation works pretty well, so we don't want to throw it away entirely, but let's build on the Galilean transformation to figure out what the new correct transformation is. So remember, Galilean transformation, x prime equals x minus vt if the moving frame is moving in the x direction. So we'll still have the moving frame moving in the x direction because these are still inertial reference frames. We still need a frame of reference to be moving at constant velocity, so there is still no loss of generality to just call that the x direction, or the y direction, or the z direction, but in this case, let's call it the x direction. And then we can just change the letter x to y or z if the moving frame is moving in the y or z direction. But the Galilean transformation tells us this: x prime equals x minus vt. We don't have a transformation in the y or z direction because the moving frame is moving in the x direction. Galilean transformation also assumes, without even discussing, that time is absolute, time is the same in all reference frames, and therefore we are able to conclude the relationship between the velocity transformation. And then you could also write down the acceleration transformation, a prime equals a. Excuse me. So what we will see is how this changes. This the position transformation changes, but again, this is going to still be okay, and this is going to be okay. This changes. This changes. Okay, and this is going to be okay. So we'll see. Let's see what we do with the Galilean transformation. So in order to derive the new transformation, Einstein wanted to think about the Galilean transformation, x prime equals x minus vt, and the inverse transformation. Remember, the inverse transformation is just how do we go from the prime frame back to the unprime frame. That's just x equals x prime plus vt. Except that, right? So this is the first is transformation to transform from the unprime frame variables to the prime frame variables. The second is how to transform from the prime variables to the unprime variable, except for Einstein recognized that the time is no longer absolute. So if we're going in the second one, the inverse transform is from the prime variables to the unprime variables, then it's going to be t prime, right? So we've got t prime, because no longer is t prime equal t. X, nix. Okay. So this is the transformation, and this is the inverse transformation. These are still Galilean transformations. Okay, but what Einstein said is, okay, well, the Galilean transformation may not be right, but it's got to be approximately right. So we're just going to multiply it by a linear factor. We're going to we're going to multiply it by an arbitrary constant gamma. Or actually, gamma in the unprime variable and gamma prime in the prime variables. Again, just make sure we understand that v, there is no v and v prime, right? V is the relative velocity. And the relative velocity, if one is moving at v relative to, if frame O is moving at v relative to frame O prime, then frame O prime is moving at v relative to frame O. There's no transformation there. So what Einstein said is, we got to change it, but how do we change it? Well, first of all, we still have to have a linear transformation. What do I mean by that? We still have to have a linear transformation. What I mean by that is that for any one event in the unprime frame, there can only be one event in the prime frame. In other words, we can't put a squared on this, right? We can't square something, because now that makes two events in one frame are equal to one event in another frame. That there's one event in one frame would mean that there are two possible different events in another frame. So it's got to be linear. Hence, we simply multiply it by a factor. And he's just giving it arbitrary factor. We got to solve what that arbitrary factor is. And the other thing that Einstein recognized is, if we're going to modify the Galilean transform, we're going to multiply it by some arbitrary factor. And what is the relationship between gamma prime and gamma? What he recognized is that must be the same, because it doesn't matter which frame is x and which frame is x prime, right? We could just go ahead and rename. We could rename this the first frame O prime and the second frame O, and so then the equations would be reversed, right? So gamma must equal gamma prime. Those two can't be any different. Otherwise, it wouldn't make sense that there's no preferred inertial frame. Okay, no preferred inertial frame. That's not really. Let me write this down. Right, that it doesn't matter which frame we start from and which frame we transform to. We should still have the same factor. Okay. So now let's just summarize. Einstein now has the transformation from O to O prime. He's got the inverse transformation from O prime back to O. And we've got these two equations. And the difference now is that the Galilean transformation we're keeping it linear, but we're saying, well, maybe we need to multiply it by some factor in order to improve it. And we are also saying that time is not absolute. Okay. Then Einstein also recognizes, and he's going to apply postulate 2. Postulate 2 says that the speed of light is the same in either reference frame. So if speed of light is moving in the prime reference frame, we will measure a distance that the light has moved equal to the speed of light c times the time t prime, which is now the time measured in the prime frame, or the same for the unprimed frame, right? A distance measured in the unprimed frame is equal to the speed of light in the unprimed frame times the time in the unprimed frame. Okay, so this is just a distance that light would move in either frame. But because of postulate 2, these two c's are the same. It's not c and c prime. So we can go ahead and plug that in to the Galilean transformation and say that therefore ct prime is equal to gamma ct minus vt. And ct is equal to gamma ct prime minus vt prime. We call those equations C and D. Okay. And now we just solve these four equations together, A, B, C, and D, for gamma. So remember, gamma is the new thing here. T not equal to T prime is a new concept, but those are just two different times we measure in two different frames. Gamma is this unknown number that we are allowing the Galilean transformation to be more general by multiplying it by some arbitrary constant gamma, but it still has to be linear in order for what events to be one-to-one. Okay, so that's where the gamma comes from. Okay, so we solve. I'm not going to do the algebra. We solve for gamma. This is just algebra. Plug and chug. Solve these all together so that you get gamma, and it turns out that gamma is equal to something that we've seen before, 1 minus v squared over c squared, or often written as 1 over the 1 minus beta squared. Because beta comes up so much, we write beta as v over c. So this gives us our new transformation, right? Our old transformation, our one-dimensional position variable was that, where gamma is equal to what? The old transformation, the Galilean transformation, what's gamma equal to? It's equal to 1. In the new transformation, gamma is no longer equal to 1. It's equal to this quantity here. Now, what if v is so much less than c that we can use the 0th order approximation? What is this value approximately equal to if v is so much less than c that we can use the 0th order approximation? Gamma is equal to 1, right? And that's the concept that we should simplify, that the new transformation better simplify to the old transformation for slow speeds, right? For v not like c. Gamma is equal to 1 gives us back the Galilean transformation. What is the range for gamma? What are the possible values for gamma? Well, let's go back and ask, what are the possible values of v, right? C is a fixed number. What's the possible values of v? V, remember, is the speed of the reference frame. So it's like saying if we're in the lab and our speed is 0, but we get into a car, right? The speed, and that's a new reference frame. We get into a boat, we get into a plane, we get into a spaceship. V is the speed of our reference frame, right? It's the speed of an object that we're riding along with. It's the speed that we can give a mass, right? So V, what are the ranges of speed for V? V can be anywhere from 0 to c. Inclusive of 0, not inclusive of c. Why is that? So V can be 0, right? We can compare the lab frame to another lab that's not moving relative to our first lab. That could be V. That could be V equals 0. And then V could be a moving object relative to the lab. But what's the fastest that something can move? We will see from this new transformation that the fastest an object can move is actually less than c. But that's also just one of Einstein's conclusions, that c is this universal speed limit. Nothing can travel faster than the speed of light. Speed of light is the fastest possible speed. But we'll prove this later. But these are the ranges of V. These are the ranges of V. So what happens when V approaches C to gamma? Okay, again, when V is equal to 0, gamma is equal to 1. But what happens when V approaches C? When V approaches C, what happens to gamma? Gamma goes to, if V is equal to C, then you've got 1 minus 1 in the denominator, and you got a 0 in the denominator, and so you got infinity. So gamma approaches infinity. So gamma can be any quantity between 1, oops, that's a 0, 1 and infinity. Gamma's from 1 to infinity. And what's beta? Beta, if V is equal to 0, beta is 0, and V equals 1, beta is 1, right? So beta can go from 0 to 1. Gamma can go from 1 to infinity, and beta can go from 0 to 1. It's important to understand those limitations. Hopefully you caught this a long time ago. This was supposed to be a positive. That was a positive when we wrote it down on the previous page. And so this is a positive. And that makes the signs work out correctly. Just doing the algebra, figured out the signs weren't working. Okay, so this is our new transformation. Oh, again, we got a sign error here. Okay, so this is our new transformation. What else can we conclude? Well, we can conclude that y prime equals y and z prime equals z because we're only transforming the x and the t. But what else can we conclude? Well, we can also solve for t prime. We want to see how t transforms now, right? We've got x, y, and z, but what about t? We can solve for t prime. We can take the inverse transform, the second equation, and we can solve for t prime, right? So there I just solve for d prime in the first line, and then I take the transformation for x prime and plug that in on the right-hand side so that I have all unprimed variables on the right-hand side, so I can do a transformation from unprimed variables to prime variables. And now I do some algebra. And I write out the algebraic steps because this is the kind of algebra, it's really not hard. It's the kind of algebra you have to do, but I see students getting stuck on all the time. You just got to start writing things out and plugging them in and seeing what you get. So anyway, I'm doing the steps of algebra. So the first line, I've just plugged into the inverse transform. I've plugged in going from the first line to the second line, I plugged in what x prime is. Going from the first line to the second line, I plugged in what x prime is. And then going from there, it's an algebraic simplification. It's a further algebraic simplification. Simplification, I don't know. I've just, in the third line, I factored out as gamma. In the fourth line, I multiplied through by the 1 over v that I had. And then I need to take this constant, which is, it's a constant, gammas and v's, and I need to simplify it. So there you go, right there, it's simplified. And it simplifies to minus v over c squared if you write it out, because gamma is 1 over 1 minus v squared over c squared. So we write that out, and I would defy you to do this algebra. You've got to be able to do it yourself. Plug that back in, and we get the transformation for t prime. So we now have a transformation for t prime from the unprimed variables because time is no longer invariant between frames. So our new transformation, I'm going to write it out like this. And I will note that we haven't yet looked at it, but that u prime is no longer equal to u minus v. And that's a little bit of a surprise, but we'll see why if you can't guess or if you haven't read ahead. We'll get to that later. The other thing I want to point out is that these are often written as instead of the position relative to 0, we often write them in terms of delta x prime, which would be x2 minus x1, the distance between two things, the distance between two events, right? And we often talk about events when talking about special relativity, like the event of what happens. The event is I walk through the door, therefore you look. I turn off the light, therefore it gets dark, right? How long between the event of I turn off the light and it gets dark, is how long it takes the light to travel from the light to the floor, etc. So anyway, two events. So we often write this instead of as x prime equals gamma x minus vt, we write it as delta x prime is gamma delta x minus v delta t, and we write delta t prime is equal to gamma delta t minus v over c squared delta x. You can write it either way, it doesn't matter. Delta y equals delta y prime, delta z equals delta z prime. But u prime is still u prime. Okay, we'll get to that later. So this is our new transformation, and it is called the Lorentz transformation. The Lorentz transformation abbreviated Xform. Let's see what this Lorentz transformation does for our physics.